Learning which choices are good to make from the instruction of others is more time and cost efficient than learning via trial and error. However, people will persist with choosing according to inaccurate instruction in the face of instruction disconfirming feedback, and this bias towards instruction is termed instructional bias. So the mechanisms underlying instructional bias are debated, with three competing models arising in the literature. In the learning override model, learning is unaffected by instruction but is overridden at choice. In the learning bias model, learning is bolstered for instruction congruent outcomes and suppressed for instruction incongruent outcomes, so learning is biased towards the instruction. And lastly, in the learning suppression model, learning is generally suppressed for the instructed item. So these inconsistencies in the literature may result from instructional bias being measured as subjects make value-based decisions. This may make it difficult to separate instructional effects on learning from instructional effects on choice. But prior work showed that neural activity in early visual cortex measured during a value-independent perceptual judgment task was sensitive to object value after learning. So based on this, between intervals of learning, we aim to use pattern analysis of early visual cortex activity to track learning in the brain independent of choice and distinguish between these models of instructional bias. So in the task, subjects learned the value of 6 abstract visual stimuli, where value is the proportion of trials on which a choice of the stimulus is correct. And these stimuli are randomly assigned to one of 3 training pairs, such that within each pair there is a high and low value stimulus, and the difference in values in the CD and EF pairs are the same. But crucially, subjects are always instructed that the low value D stimulus has the best chance of being correct. So in training blocks, the stimulus pairs are presented, and subjects must choose the item they think is most likely to be correct, and they receive feedback for their choice such that the stimulus values can be learned. Test blocks are very similar, however, subjects are presented every possible pair of the 6 stimuli, so for example A with F, and they receive no feedback for their choice, preventing them from learning further. Subjects also complete blocks of a size judgment task in which they simply have to press a button when the stimulus changes in size relative to the previous trial. So during the size judgment blocks, we get a measure of neural activity in early visual cortex for each of the stimuli that should not be influenced by current value-based choice behavior. So if the neural responses for each stimulus have tuned according to value of learning, the size judgment blocks should allow us to cleanly measure this learning. So after receiving the instructions, subjects complete cycles of training, size judgment, and test, and this cyclic structure allows us to characterize how neural activity has sensitized to value at different points in learning for each of the stimuli. So we collected behavioral pilot data from 15 subjects and showed instructional bias effects in the training and test phases. So this replicated past work that used this task. But the main aim of this project is to assess whether the neural activity in early visual cortex reflects value differently for instructed and uninstructed stimuli. And we plan to do this using either a pattern-similarity or a classification-based analysis. So with the similarity-based analysis, we can see whether neural activity reflects unbiased or biased object values represented by 2 behavioral dissimilarity matrices. The raw stimulus values are used to compute the unbiased matrix, and the bias matrix is computed using the same values, only the D stimulus is treated as being higher value, so that's correct on 60% of trials instead of 40%. For each of the 5 size judgment blocks, we will then compute the dissimilarity between patterns of bald activation for each of the 6 stimuli. And we can then correlate each of these patterns with both the unbiased and biased dissimilarity matrices to see whether neural activity appears to be reflecting the unbiased or biased values of time. With the classification analysis, we can assess whether neural activity while viewing the instructed stimulus becomes similar to the neural activity while viewing the very high and low value stimuli, so that's A and B. Assuming that neural activity in early visual cortex does indeed reflect value of learning, the rationale behind this is that if a classifier is trained to classify neural activity as either A or B, then with learning, a higher value object, such as E, should be classified more frequently as A than as B. And we can use this to infer on each size judgment block whether the neural response to instructed stimulus D is becoming more similar to A, and this would be biased learning, or to B, and this would be correct learning. So due to the pandemic, we have not been able to collect fMRI data, but I will explain the hypothetical results for the 3 competing models. In the learning override model, learning is not biased, it is overridden at choice. So learning would be equivalent for the instructed and uninstructed items. Therefore, for the pattern similarity analysis, we'd expect neural activity to correlate more with the unbiased values throughout learning. For the classification analysis, we'd expect classification accuracy for both instructed and uninstructed stimulus trials to increase at the same rate. This would suggest that subjects are learning D and F are both low value despite them expressing an instructional bias towards D in their choices. In the learning bias model, learning is biased towards instruction. Therefore, for the pattern similarity analysis, we'd expect neural activity to correlate more with the biased values of learning. And for the classification analysis, we'd expect instructed stimulus trials to be initially inaccurately classified as A, whereas for the uninstructed stimulus trials, classification accuracy would only increase. This would suggest that learning for the instructed stimulus is specifically being biased. And lastly, in the learning suppression model, learning is generally suppressed for the instructed stimulus. So since there could be some learning towards the unbiased values for the instructed stimulus, the pattern similarity analysis may show neural activity to correlate slightly more so with the unbiased matrix, but the difference between the unbiased and biased correlations should be small. Similarly, for the classification analysis, classification accuracy for neural activity while viewing the instructed stimulus should increase, but at a lower rate.